let's recall what we were doing at the end of last time. We were looking at bundles with discrete structure group. And I remind you that we argued that they're classified by the monodromy representation. So if we choose some point x naught here, then if E is the total space of the bundle, then above x naught, there'll be the fiber, E sub x naught. And if we choose a point in the fiber, call it E naught, then we've trivialized the bundle, at least at that point, because now we can say that corresponds to the identity group element, and then we have a principal homogeneous space for gamma. And now, if we have a closed curve, sigma of t, then by the homotopy lifting property, if we say that the initial point of our lifted curve starts at E naught, then there's a unique lifted curve, sigma tilde of E naught, and it will do something projecting down to sigma under the projection e to x, and then the final point here will be E naught dot G sub E naught sigma. And G sub E naught sigma only depends on the homotopy class of sigma with fixed endpoints, and that is pi 1 of x at x naught. And moreover, I showed that if I compose curves, then these monodromy group elements multiply, and therefore, to a gamma bundle, we associate a group homomorphism in xx naught into gamma. If I change my choice of E naught, I conjugate this homomorphism, and so we should mod out by conjugation, and then this gives a description of the principal of the isomorphism classes of principal gamma bundles on X. So that's what we showed last time. Okay. Now, let me just make one little remark. I'm going to generalize that a bit. But one little side remark here. If gamma is abelian, then you see any homomorphism from pi 1 into gamma has to factor through the abelianization of pi 1. Now, pi 1 can be non-abelian. We'll discuss Riemann surfaces a little bit, where it's generally non-abelian. And so what I'm saying is that if gamma is abelian, then you see, if I look at sigma 1, sigma 2, that's chi of sigma 1, sigma 2, which is chi of sigma 2, sigma 1, because gamma is abelian, which is chi of sigma 2 composed with sigma 1 because chi is a homomorphism. And so chi behaves as if it's, and so, say that more precisely, and so sigma 1, chi is sigma 1, sigma 2, sigma 1 inverse, sigma 2 inverse is equal to 1. And that means that chi is equal to 1 on the commutator subgroup, and therefore passes to a homomorphism called chi bar on the factor group. Okay, and the factor group has a name. This is the first homology of X. It's an abelian group. And so what we get here is that the principal gamma bundles on X can be identified with hom of H1 of X into gamma. You see, also we're supposed to mod out by conjugation, but think about it. If gamma is abelian, then of course conjugation is trivial. The action of the group by conjugation is trivial when gamma is abelian. And so this is equal to, this is also known as the first cohomology of X with coefficients in gamma. Now, this being an abelian group, you could ask the question, is there a natural abelian group action on principal gamma bundles over X? And indeed there is. You see, if I have two of them, P1 and P2, I can take what's called the fiber product, pi1, pi2, which is the space of points P1 and P2 which project to the same X. And so this is a principal gamma times gamma bundle. Tell me if I'm going too fast. This is a principal gamma times gamma bundle. And now we can divide by the right action of gamma diagonal. And now again, using the fact that gamma is abelian, this is a principal gamma bundle. So what I'm saying is that if I take the fiber product divided by gamma, the diagonal subgroup, then that is a principal gamma bundle. And I'll leave it to you to check that under the abelian group law on this abelian group, the monodramy of this guy is indeed the sum of the monodramies. Okay? That's a little exercise. Now, in the special case of gamma equals Z2, that's a rather important case. Certainly Z2 is an abelian group. And so then what we're talking about here are twofold covers, double covers of X. Okay? And in this case, what we're saying is that for every principal Z2 bundle, we get an element of H1 of X with Z2 coefficients. And this assignment of a certain cohomology class to a principal Z2 bundle or a double covering, this is called a characteristic class. And it has a name. It's called the first Stiefel-Whitney class. Okay, and it's denoted W1 of P. Okay, so this is a perfectly fine definition of W1 of P. Now, given a manifold M, so I'm replacing X, which could be any space, by a manifold, there exists a canonical double covering. Let's call it M tilde equals P. Called the orientation double covering. see, what you can do is if you have a manifold, you can take your point M on the manifold, and then there's always a tangent space there, d sub M of the manifold, and that's a vector space. And now you see, a vector space always has two orientations. Okay, I'm talking about a real vector space, and a real vector space has exactly two orientations. Now, I'm not going to give a formal definition of orientation, but I hope everybody has his or her own understanding of what an orientation is. We could think about ordered bases up to the action of the orientation preserving transformations, S, L, and R. Okay, so we have two orientations, and that defines a double cover. So over this point M, we have the orientation plus and the orientation minus of the tangent space. So they project to this point, and then as we move the point around, we get a double cover. So every manifold has a canonical double cover called its orientation double cover. Okay. Now, if M is orientable, what does that mean? That means that I can consistently choose an orientation smoothly, continuously choose an orientation as M, little m, moves around my manifold. And what is that doing? That is, you see, a global section of the orientation double cover, which we just agreed is a principal Z2 bundle. But you know that that means that the principal Z2 bundle is trivial, because we proved that a principal bundle is trivial if and only if there exists a global section. So if M is orientable, there exists a global section. M tilde to M is trivial, and hence W1 of M tilde is 0. Okay. And moreover, note that M tilde is necessarily disconnected. Because, after all, if I can choose one orientation, then of course I could have also chosen the other orientation. And those are disconnected. Now, if M is connected, but unorientable, okay, then W1 of M tilde will be non-zero. I will not be able to choose a global section, okay, and therefore M tilde is connected. So you see, if I take a two-dimensional sphere, the orientation double cover of the two-dimensional sphere is two copies of the two-dimensional sphere with the opposite orientations, disconnected. If I take RP2, or a Klein bottle, the orientation double cover of that is going to be a connected surface. So for example, for RP2, we've already seen this many times, S2 would be the orientation double covering. That would be our non-trivial Z2 bundle over RP2. And for the Klein bottle, if you think it through, the orientation double cover would be a torus. Final thing to say here is that for this canonical double covering, what we usually say is that the first Stiefel-Whitney class of the manifold M is by definition the first Stiefel-Whitney class of this particular double covering of M called the orientation double cover. So we'll talk about characteristic classes in more generality. Of course, there are higher Stiefel-Whitney classes. The one there is not just for ornamentation. There are many Stiefel-Whitney classes, and they measure other things about manifolds. Okay. Now, I started all this by talking about principal bundles with a discrete structure group, just the way fiber bundles can be generalized to fibrations. We can apply that in this case too, and that leads to the notion of covering spaces. So a covering space is by definition a fibration with discrete fiber. And now, basically the same construction that I explained last time goes through. You have the covering homotopy property, you have the lift. The only thing you don't have is a principal homogeneous space at every point, but you still have a monodromy transformation. Now, an alternative definition of a covering space that you'll often see is that a covering space is a map P from x hat to x such that around every point in X, there exists some neighborhood, let's call it V, so that P inverse of V is a disjoint union of V tilde alpha, let's say, where each V tilde alpha is homeomorphic to V. So the picture is, here's X, here's V, here's X hat, and around any point you can find a V sufficiently small so that you have these disjoint copies of these V alpha hats, V alpha tildes hats, whatever. The equivalence to this definition, that it's a fibration with a discrete fiber, is easily seen by just taking a point and thinking about lifting paths as the paths explore some local neighborhood V. And given any covering, we can define a covering group. The group of automorphisms of the cover is the group of maps phi that commute with the projection like this. Then phi is called an automorphism of the cover. Clearly, if I have two phi's, I can compose them, and it's again an automorphism of a covering. So the automorphisms form a group, and this is called the group of deck transformations. Okay. Now, we saw before from our exact sequence that because the covering is discrete, because the fiber in a covering is discrete, pi 1 of x hat, let's say with some lifted point x naught hat, into pi 1 of x, x naught goes to pi naught of our fiber. So this injects into this. So pi 1 of x hat injects into pi 1 of x. And I want you to have the intuition that that means that taking a covering dilutes the fundamental group. It makes it smaller. You see, this could be a bigger group than this one. This injects into here. So you lose nothing. Everything from here goes into here. Okay? I'm saying that algebraically. Geometrically, as there's a non-trivial loop upstairs, Okay, it's going to project to a non-trivial loop downstairs. That's what the vibration, that's what this exact sequence is telling us. So covers dilute pi 1. Well, you might ask, can you dilute pi 1 completely? And the answer is yes. So there's a distinguished, given any topological space, sufficiently connected, so I'm not going to go into the mathematical technicalities. It's got to be arcwise connected and something called locally arcwise connected, but anything you're likely to meet will satisfy that. So given a topological space X, there exists a canonical cover called the universal cover. Okay, so the theorem is, given X, arcwise connected, and some other fine print, then it has a universal cover, X tilde, with pi 1 of X tilde equal to pi 1 of X tilde equals 0. Okay? So you can always dilute away the fundamental group completely. And we've essentially seen most of the key ideas here. Because remember that if I had a space X and I chose a base point, I could define the path space of X. Okay? Remember what the path space of X was. It was the set of all paths P, I guess I'm going to call them alpha. All paths alpha from 0, 1 into X, such that alpha of 0 starts at our base point, and it can go anywhere it likes. Okay? So here's X. Actually, let me say here is X. Here's X naught. And now I just let my alpha go wherever it wants. This is X naught, where alpha equals 0. Alpha is 0. All right. And this path space has a canonical base point. I should have called this alpha naught. Alpha naught is equal to the constant path at X naught. Very boring path. It just sits here for the time 0 to 1. Okay? That's a base point in the space of paths. Now, all we got to do is quotient this space in order to get the universal cover. All we have to do is take an equivalence relation where we mod out by homotopy with fixed endpoints. Okay? That's going to be our universal cover. So supposing X has a hole in it, then if I have two alphas and alpha prime here, up in X tilde, they're, let's say this is ending at some point X1, then they're defining the same point in the universal cover. Okay? But if I have a path, say, going over to some X2 here, an alpha like this, and beta like that, ending at the same point X2, then in the fiber over that X2, we might have an alpha, or I shouldn't call it alpha, have an epsilon and a beta. You see, those are homotopically different paths, okay, with fixed endpoints. And so their homotopy classes correspond to different points in the universal cover over this point x2. Now, clearly, there is a projection from x tilde to x. What it does is it takes the homotopy class of alpha and it takes it to the point alpha of 1, the endpoint. Okay? All right, now, as we observed before, in the path vibration, the fiber above x naught are the based loops at x. So, in the universal cover, the fiber above, this is in the path vibration, in the universal cover, we mod out by homotopy, and by definition, that's xx naught. If we chose, so this has a distinguished endpoint, and so we've actually trivialized our fibration over that point. But if we chose another point, like this one, well, you see, the fiber over this x2 can be put into 1-1 correspondence with pi 1 of xx naught, because you could choose some reference curve from x naught to x2, and then every other curve you could concatenate to make a closed curve and associate its homotopy class. Okay? But of course you made a choice there. And so there isn't a canonical way of deciding which of this, whether this purple or this pink is the base point. So there's no canonical base point. But still, the different points up here correspond, can be put into 1-to-1 correspondence with the elements of pi 1 of xx naught. Okay.
A question.
Yes?
Much the same way as with a discrete fiber, would a choice of canonical base point be equivalent to picking a trivialization of the universal?
That's absolutely correct, yes. But you see, that's the point I'm trying to make, which is, while there is a canonical trivialization here, we don't have such a canonical trivialization at any other point. Okay, so we have this covering space, and now let's look at our exact sequence. So we have pi 1 of x tilde x naught. Yes?
Why is pi 1 of x tilde 0?
It's exactly what I'm about to explain. So this is the exact sequence. So we go, here I'm just writing what we had before. Okay. Let's say x is connected, so this goes to 0. The kernel of this map is just 0, so I can put 0 here. The fiber is this discrete group, pi 1. So this is just equal to pi 1 of xx naught. Okay? But that means that this is an isomorphism, because I have the same group here and it's an onto map. And that means that this is equal to 0. And so that answers your question. So that's the proof that, in fact, pi 1 tilde is 0. Of course, all the other higher homotopy groups are the same. Again, by our sequence. In fact, this x tilde over x is a principal fibration. This is a principal fiber bundle with group pi 1 of xx naught, of course. And what's the right action? The right action is, if I have homotopy class of a path alpha from x0 to somewhere, and I have an element of pi 1, I simply take this to alpha proposed with sigma. So in other words, I first do whatever sigma has to do, and then I do alpha. That gives me a new path from x0 to x1, and that's the right action. So the group of deck transformations is equal to pi 1. Now, why is it called the universal cover? Because of something which is called the Galois correspondence. Every other covering space is obtained from this one by quotienting by some subgroup of pi 1. Because after all, you could take any other covering space and you could take its universal cover. So if you have some other covering space, x hat, you have a diagram like this, where x hat is now x tilde mod gamma prime, where gamma prime is a subgroup of pi 1 of x naught. So this is called the Galois correspondence. It's very beautiful. It means that the covers are in one-to-one correspondence with the subgroups of pi 1. Now, in general, x hat to x is not a principal bundle. But if gamma prime is a normal subgroup, then the fiber here is gamma mod gamma prime. That's another group. And so for normal subgroups, we actually have a principal bundle. So now I hope it's clear why this notion is actually a notion of a generalization of principal bundles with discrete structure group. There's actually a deep analogy here with the theory of Galois extensions and number theory. So let me just comment on that very, very briefly. If you have a polynomial equation like this equals 0, where the a sub k's are integers or equivalently rational numbers, then you could look at solutions of this over the complex numbers, and that gives you some set of roots, theta 1 through theta n. And if you extend the field Q by those, then what you get is a field extension. And then there's a Galois group which permutes these different roots. And the different field sub-extensions correspond to subgroups of this Galois group. So this should sound familiar. And the way the analogy goes is that you should think of these field extensions as corresponding to the fields of functions on these spaces. You see, let me just make the very trivial remark that if x hat over x is a covering space, then there are, in some sense, quote, more, some heuristic sense, there are more functions here than there are here. Because after all, if I have any function here, I could pull it back and get a function here. Right? But it's not always true that a function here comes from a pullback down here. So the field of functions up here is going to be an extension of the field of functions down here. So there's a very deep analogy with number theory here. And so this Galois correspondence under that analogy corresponds to is the Galois correspondence of number theory. The analog of the universal cover of the field Q would be, the universal cover would be what's called Q bar, the field of all algebraic numbers. Okay, the other thing I wanted to say about the universal cover is that it gives us another perspective on our theorem that principal gamma bundles on X correspond to homomorphisms of pi 1 X into gamma mod conjugation. And the way that goes is the following. You see, in fact, in arguing this, I left something out. I never showed you that if I have a homomorphism chi, I could actually construct a principal gamma bundle over X whose monodromy was given by this homomorphism chi. So now I'm going to do that. Okay? And the construction is one of these tautological things. So suppose we have such a homomorphism, chi from pi 1 x naught into gamma. Well, I'll construct the following principal bundle. P sub chi will be the universal cover times over pi 1 of x naught gamma. And what this means is the following. Our equivalence relation here is alpha comma gamma is equivalent to alpha composed with sigma chi of sigma inverse dot gamma. Or another way of saying this is that alpha composed with sigma comma gamma is equivalent to alpha chi of sigma dot gamma. So you see, I take the product space, x tilde times gamma, and then I divide that product space by this group pi 1, imposing this equivalence relation. Now, we've got lots of other things to do, and the details are in the notes, so let me just say that, okay, the obvious projection to x here is to take this thing, let's say a little more about this. Okay, so P sub chi is the set of these equivalence classes of alpha, alpha considered as a point in the universal cover, and gamma. And we can project that to x by taking this guy and mapping it to the end point of alpha. Okay. So that's a projection. And the fiber, I leave it to you, get this through, is gamma. Or rather, better to say, the fiber is a principal homogeneous space for gamma. And moreover, the monodromy, sort of tautologically, if you think it through, is exactly chi. Okay. So that's one explicit construction of a bundle with prescribed monodromy. Okay. Right. Okay, so let me give you an example. Nice example of covering space theory. Comes from Riemann surfaces. Are there any questions about the general things I've said?
The prin gamma of x, when I think about it, I want to think that these are isomorphism classes.
That's the way to think about it.
Yeah.
So this is the set of isomorphism classes of gamma bundles on X.
Right.
Not actual bundles. To get actual bundles, well, all sorts of things. You have to give an actual bundle. Okay, so Riemann surfaces. So first of all, what is a Riemann surface? So for me, a Riemann surface is going to be a two-dimensional, manifold, oriented, manifold with a complex structure. That's one way of thinking about a Riemann surface. Or another way of thinking about it is a two-dimensional, two real-dimensional manifold, which is oriented and has a conformal structure. A conformal structure means a metric, g mu nu, dx mu, dx nu, up to Weyl transformations. So those two notions turn out to be the same. Now, and we have a groupoid of these things, so we have invertible morphisms between them, which are holomorphic isomorphisms, or maps between manifolds that are conformal, that pull back the Riemannian structure on one to the other up to some rescaling, some Weyl transformation. So there's a famous theorem, which we're not going to prove, which says that up to conformal isomorphism, the only simply connected Riemann surfaces are CP1, C, and the upper half plane. The set of Z such that the imaginary point of Z, imaginary part of Z is positive. Now the upper half plane is conformally isomorphic to the unit disk, the set of, let's say, W, such that the absolute value of W is less than 1. You can think of it either way.
So you mean smaller or equal?
Oh no, smaller.
So it has no boundary. Don't think
That it does not have a boundary, no. Yeah, because I'll comment on why in a moment. So the theorem is that those are the only simply connected manifolds, Riemann surfaces. And so now that means that if we have any Riemann surface, we can take its universal cover. Its universal cover would have to be a simply connected Riemann surface, and so its universal cover must be one of these guys. So now you can ask, what are the conformal automorphisms of these three spaces? And this is something I always do in my group theory course. Many of you are in that course. I'm not going to review that. So we have SL2C acting here. And the other thing I do in my group theory course is classify the discrete subgroups of SL2C. There's an ADE classification of those, as many of you saw. And if we act on this with those ADE groups, we get fixed points. So we get interesting orbifolds, but not Riemann surfaces. If we look at the conformal automorphisms of this, we just get translations. So we can divide by Z plus Z, and that gives us tori. Well, tori are very interesting. But the really exciting stuff happens when we look at H. So the group of conformal automorphisms of the upper half plane is PSL2R, acting by Mobius transformations. And indeed, if sigma is a Riemann surface with negative Euler character, then its universal cover is the upper half plane, and it is equal to the upper half plane divided by gamma, where gamma is some discrete subgroup of PSL2R. So immediately we learn that pi k, the homotopy groups of Riemann surfaces for k greater than 1 are all 0. You see, because the universal cover is contractible. And I explained to you that the higher homotopy groups of X are the same as the higher homotopy groups of its universal cover. So that might or might not have been obvious to you, that the higher homotopy groups of something like this are all trivial, but they are. And this should remind you of something. We have a space here, H, with a group gamma acting without fixed points, which is contractible. Have you seen that before? It's a classifying space, right. So we learned that H is E gamma, and the Riemann surface is B gamma for these discrete subgroups of SL2R.
Excuse me.
Yeah.
So where does the conformal structure in this come? You're classifying.
Yeah. So I was going to comment on that. Yeah, right now is a good place to do it. So, very good question. Where is the conformal structure here? Well, you see, PSL2R has this remarkable property, not true in general. This is a really special thing here, that there are infinitely many ways of embedding a discrete group isomorphic to gamma, namely, let me put this better, infinitely many ways of embedding pi 1 of sigma, with respect to some base point, into PSL2R as a discrete group. And so those, you can continuously change that embedding. And that's changing the complex structure. So there's a single pi 1. In fact, let's work out what is pi 1. Well, supposing we choose a point B naught here. This is where colored chalk would be very useful. Okay. Let's take this point B naught, and now let's choose some curves. So, okay, and let's imagine cutting open this surface. Okay? Then what are we going to get? Well, I claim we're going to get something like this. Okay, where all of these points here correspond to B naught. And I should make the identifications like this, and so on. Okay, so that means if I give these curves names, let's call this A1, what do they call it in the notes? Alpha 1. Alpha 1, beta 1, alpha 2, beta 2, alpha 3, beta 3, alpha 1, beta 1, alpha 2, beta 2, alpha 2, beta 2. You see, my surface is now contractible when I make this cut, and therefore, alpha 1, beta 1, alpha 1 inverse, beta 1 inverse, alpha 2, beta 2, alpha 2 inverse, beta 2 inverse equals 1. And that's the only relation. And so, pi 1 of sigma is equal to the group which is generated by alpha I and beta I, such that the product over I equals 1 to the genus of the group commutators equals 1. Oops. So that's a discrete group. That's an abstract discrete group. Okay? Now that abstract discrete group can be embedded into PSL2R in continuously infinitely many ways. Each time you have such an embedding, PSL2R acts without fixed points on the upper half plane. You can take the quotient and you get this Riemann surface. But if you take different embeddings, you get the Riemann surface with different conformal structures. Now, by the way, we could, of course, add some punctures here. Supposing we add some punctures. We make the punctures white. And then we could add some further curves around the punctures. And that would just be taking points like this. And then our cut system would look like this. So if I call my punctures gamma 1 up to gamma k, then I modify my relation here that way. So again, I can certainly have punctures on my Riemann surface. All right. So I haven't proved a lot of important statements here. I'm just telling you what some of the theory looks like.
Is there a motivating way to visualize these embeddings, or is it just something you have
Actually, it's remarkably hard to find the explicit embeddings. People who specialize in tight fillet theory and the moduli space of Riemann surfaces, in fact, have ways of doing that, and let me define that. The moduli space of Riemann surfaces of genus G is equal to the space of embeddings of genus G with K marked points is the space of embeddings of, let's call this group here, let's call that gamma sub GK. The space of embeddings of gamma GK into PSL2R. That's one way of thinking about the moduli space of Riemann surfaces. Okay, oh yeah, one last thing here. Suppose you want to take this Riemann surface now, and you want to make an n-fold covering of it. I'm going to use this in a remark later, maybe not today, but maybe on Monday. Supposing you want to make an n-fold covering of a Riemann surface, how would you specify that? Well, we use our theorem. Okay? What we should do is we should look for a homomorphism from this gamma GK into the symmetric group on n letters, and then you can build your covering space. I will come back to that. Okay. So much for Riemann surfaces. Now, I want to mention a generalization of coverings, of the notion of coverings, which is important, which are called branched covers. Now, the terminology is not great. A branched covering is not a covering. That's the way it goes. What is a branched covering? I didn't answer your question about the boundary here. SL2R would not act well. It would not act properly discontinuously if I included the boundary of the upper half.
We preserve the
It would preserve it, but it would act ergodically. I would get some kind of non-commutative space. That's why
You are not classifying Riemann surface with boundary. I mean, that's included.
even Riemann surfaces with boundary, I take the upper half plane.
Right. Yeah.
Okay, I take the upper half plane. If I had tried to include the upper half plane with the boundary, then the gamma would not act well. All right, branched covers.
It looks like it should.
Okay. What is a branched cover? Well, the coverings we have so far discussed in this context are called unramified coverings. And a branched cover is a map of pairs, let's call it pi, from y comma r to x comma b, where y and x are some spaces. Let's say x and y are dimension n. Spaces, and B is a subspace of X, and R is a subspace of Y, and these are dimension, these are real dimensions, n minus 2. Okay? So B is a codimension 2 space in X, and R is a codimension 2 space in Y. And what I require is that if I restrict pi to y minus r over x minus b, this is a cover in the sense that we've just been discussing. In other words, an unramified cover. And if I restrict pi from r to b, okay, remember that's what it means to have a map of pairs, this is also an unramified cover. Okay? That's what a branched covering is. So it means it's a generalization of a covering where you give yourself a real codimension 2 subspace on which something funny happens. Now, the degree of the covering, say if this is d to 1, then d is equal to the degree of the cover. In general, this will be a different sheeted number of sheets, as you'll see in a moment. And R is called the ramification locus. And B is called the branch locus. Okay. So I want to look at two examples. Okay, so example 1. This is very simple. Let D be the unit disk, and let R be the origin. And we can take the unit disk with the origin to the unit disk with the origin by taking Z here goes to W, which is Z to the eth power, where E is a positive integer. So we've seen this guy before, say restricted to the unit disk. Now you see, as long as I am not at the origin, this is a nice e to 1 cover. Right? If I have some point not at the origin, then the inverse image of that will be some inverse image rotated around by the various eth roots of unity. And so E is called the ramification index. Now, you can do that with higher dimensional algebraic varieties. And the idea is just that there's some ramification locus. You can choose local, this is complex codimension 1. You can choose local coordinates, call them Z2 through Zn, and some Z here. This Z is in the normal direction. So the ramification locus is the set of points with z equals 0. And then that's mapping to B with the same set of coordinates, z2 through zn, except it's got w here in its normal direction, and you use exactly this map here. So with branched covers of algebraic varieties of higher dimensions, it looks just like this, only in the normal bundle. Okay. Now, I want to give another example, a very rich example, where we have branched covers, which also fits nicely with our Riemann surfaces. And I'm going to use it again in an example in maybe a lecture or two. So I want to talk about affine hyperelliptic curves. Okay, so what they are is the following. It's the set of points, x and y, such that, everything's complex, such that y squared equals p of x sitting inside C2. So p of x is a polynomial. Okay. So take a polynomial, any polynomial except I need all its roots are simple. That's quite important. So that means that if p of rho is 0, then p prime of rho is not 0. And I'll denote the roots rho 1 through rho n. Okay, say the polynomial is a degree n polynomial, has n roots, and I want them all to be simple. All right, so you see, this defines a one-dimensional complex manifold. Okay. And this is a hyperelliptic curve, and it clearly has a projection to C, where I take x and y, which satisfy this equation, and I simply project it to x. Now, if x is not a root, well, then p of x is not 0, so there are going to be two values of y that satisfy this. So we have a 2-to-1 cover. Moreover, if x is not a root, then there's some small neighborhood around x where it's still not a root. Right? Because if x is not a root, then p prime of x is not 0, so there's a small neighborhood where p prime of x remains sorry. If x is not a root, then you prove in complex function theory that there's an open neighborhood around x where it's still not a root. And therefore, our cover locally looks like that. So that's our definition of a cover. So that's great. Now, suppose rho I is a root. Well, then we're going to have trouble, because then the two inverse images are going to collide. And what I claim is there exists locally a 1-1 analytic change of coordinates so that this map of pi from sigma to the complex plane is pi takes psi to eta equals psi squared, which was our basic example of branched cover. So I'm claiming this is a branched cover, and it's branched over, the branch locus is the set of roots of P. Okay, is it clear? Are there any questions? So, what we'll do is we'll make the change of variables, and eta is going to be p prime of rho x minus rho I. That is certainly a 1-1 analytic change of variables between x and eta. Now I should put eta sub I here because I have to make a different change of variables near each row I, but I don't want to clutter my formula, so let me just call it eta. Okay, so in terms of eta, what is our equation? Our equation says that y squared, well, do a Taylor series expansion of p of x around row I. So it's a root, so it starts with eta, and then there's some b2 eta squared plus bn eta to the n. So that means that when eta is small, eta is on the order of y squared. Y is small. And therefore, I could make a perturbative expansion. For those of you who do tree-level Feynman diagrams, this is just what you do. You can do now a perturbation series expansion. And so you could write this, you could invert this as eta equals y squared plus c4 y to the fourth plus c6 y to the sixth, and plus so on. So now define psi of y to be y times 1 plus c4 y squared plus c6 y to the fourth plus and so on to the 1/2 power. So that's going to be y plus d3 y3 plus d5 y5 plus and so on. And this will be a convergent series in some sufficiently small neighborhood of the origin. So, you see that psi squared is indeed eta. Okay? So I've verified the claim. I can make this analytic change of variables.
Question.
Yeah.
Before we leave this topic, for the case of, is it sensible or possible to define branch cover where the ramification index is, say, infinite, like you have like a logarithmic type branch point?
I think that's an example. Yeah. That would be an infinite branching. Yeah. A log would do that. Yeah, okay, so all right, I'll leave to the notes the you could change variables, of course, the other way around. But let me just say that. So, I mean, you could have said the following. You could have said, let eta be psi squared. We know that's the map we're trying to shoot for. And then, in our equation, y squared is what? Psi to the psi squared plus b2 psi to the fourth plus and so on. So if I define y as psi times 1 plus b2 psi squared plus and so on to the 1/2, again, that will give me a analytic expansion of y in powers of psi, and these are inverse power series to each other. In either case, I can make this 1-1 analytic change of variables so that I get exactly this kind of branching. Okay, so now you see that if I remove the branch points, we have a good topological unramified cover. This is 2-to-1 unramified, where B is equal to the set of roots, and R is the set of solutions where Y is 0 and X is one of the roots. And restricted to R, we simply have a 1-to-1 map from the ramification locus to B. Now, because we have a nice unramified cover here, we can start to look at the monodromy representation. So supposing these are the roots, we can ask, let me draw that slightly differently. Supposing this is now the complex x-plane, and we look at the roots, on the complement of those roots, we can now ask what is the monodromy transformation. So we choose some base point x naught, and we look at the monodromy transformation, and you can see, I hope, that it's just going to be -1 or as I go around each of these roots. Because you see, I go close to here, and then I go around this, think of it this way, I go here, and then I go around here, and then I come back, and as I go around this local ramified covering, I take c to minus c. Notice that you only have odd powers of y here in terms of c, or only odd powers of c here in terms of y. So c to minus c is the same as y goes to minus y. Okay? So you're changing the two sheets by this action of -1, which takes y to minus y, as we go around each of these curves. Is that clear? Let me put it differently. So this is a principal Z2 bundle. And the action of the Z2 is xy goes to x minus y. That's the freely acting Z2 on the solutions. So what I'm saying is that the monodromy around each of these simple curves is just -1. If I choose a particular route and then continuously vary x following that route, I'll come back to the opposite sign route if I go around each of these simple zeros. Yeah.
So if you have like odd number of branch points, or branch points, then the infinity is always a ramification.
I'm going to talk about infinity in a moment. So right now we're just talking about a branched cover over the complex plane. Now you're asking, can we take that complex plane and put it into CP1? And what happens there? And I'll discuss that. Okay. Now, as I stressed before, if I take unramified covers, then I dilute pi1, right? If I take an unramified cover, the pi1 gets smaller and smaller until I get up to the universal cover, and then it's 0. Branched covers can do the opposite. Branched covers can create pi1. Okay? And now I want to demonstrate that. So the way I'm going to demonstrate that is the following. Consider the differential form omega, which is dx over y. Okay, so that's a 1 form. And now you might worry, and now this is to be understood as restricted to sigma. So you can write this differential form on C2, on x and y space, and you can restrict it to sigma. So y is a function of x up to this plus or minus root. Now you might worry that this form is singular, right? Because y can definitely be 0. Where is y equal to 0? Y equals 0 is the ramification locus. But at the ramification locus, that's exactly the place where x is not a good coordinate. What's the good coordinate near the ramification locus? The good coordinate is this c. So we should make a change of coordinates. So dx is equal to, now eta is psi squared, so that's 2 psi d psi, divided by p prime of rho I. And y is equal to c times 1 plus order c squared. And this is what it looks like near x equals rho I, y equals 0. But now you see there's a first order 0 here, which cancels this. So omega is 2 divided by p prime of rho I dc 1 plus order psi squared for small psi. So this differential form is perfectly smooth at the ramification locus. And it's clearly smooth everywhere else. So it's a nice differential form. Okay. So what? Well, notice that it's also closed and holomorphic. So because it's holomorphic, I can use Stokes' theorem. And because it's closed, I can start to look about, it's interesting to look at its integral around closed curves. So let's consider two branch points, say rho I and rho j. And let's consider a closed curve here, gamma, which goes around those two branch points, but no others. Okay? All the other branch points are out here somewhere. Now, because the monodramy was -1 going around each of the individual branch points, the monodramy is +1 if I go around this curve. And what does that mean? That means I can unambiguously choose a lifting of this curve to one sheet. Okay, I can unambiguously choose a root of y as I go around this green curve gamma. If you like, I could choose a cut here, and on the complement of that cut, I can unambiguously choose y. So that means that there are two curves. Let me draw this. Let me draw it this way. So we have this here, and we have this green curve here, and then locally we have two sheets. Okay, and well, isn't that a good drawing? Well, okay, let me draw it this way. But this point is the same as this point. This point is the same as that point. This is supposed to be the preimage of this rho I. So this is rho I comma 0, and this is right here, and this is rho j comma 0. In any case, if I don't touch that, then there are going to be two inverse images. Let's call that gamma tilde plus and gamma tilde minus. And now if we look at the integral of dx over y around gamma tilde plus or minus, now with either choice, I can project it down to here, and I can use Cauchy's theorem to pull this green curve close to the cut. And so this is going to be the integral plus or minus 2 times the integral from rho I to rho j, say along the cut, of dx over the square root of p of x, where on this interval I make a definite choice of sine of the square root. Okay? And this is not equal to 0. In general. So this is a very interesting thing. You see, these are called the periods of the hyperelliptic curve sigma. And you see, they're just functions, if you like, of the polynomial. If you've got the polynomial, you know its roots, so you know its rho i's, and that's all that went into here. So this is a function of the polynomial. Now, what about this gamma tilde? does gamma tilde plus or minus bound a disk in sigma? Certainly gamma bounds a disk in C. Well, you see, if gamma tilde bounded a disk in sigma, then, so if gamma tilde plus, let's say, was the boundary of some disk, that's called d tilde plus, then by Stokes' theorem, omega would be equal to df for some well-defined function on the disk, and then the integral around gamma tilde of omega would be the integral of df, which by Stokes' theorem would be, I guess it's by Stokes' lemma and by Stokes' theorem, this would be, sorry, this would be equal to 0, because f would be well defined. Sorry, getting ahead of myself here. Yeah, I actually don't need this. If df, if omega were d of a well-defined function, this would just be the line integral of a well-defined function. All I'm trying to say is that because this integral is non-zero, this gamma tilde cannot, excuse me, all right. If gamma tilde is the boundary of a disk, then by Stokes' lemma, there we go, then by Stokes' lemma, omega is an exact differential. But I really need it to bound a disk. Then if it's an exact differential, its integral around this contour would be 0. So the conclusion is that if the period is not 0, then gamma tilde plus and minus are not contractible. And they don't bound disks. Okay? So, as I said, branched covers can create pi 1. In fact, we can get a good picture of what's going on here by the following drawing. So let's choose our two covers of the complement of the roots where I now choose a system of cuts. And let's assume that the degree of P is even, let's say 2m. Okay? So then I have zeros. Like so. And if I choose cuts, then on the complement of the cuts, I can choose unambiguous solutions y. Okay, so let me just draw those two surfaces for those two values of y plus and y minus. They both exist unambiguously on the complement of the cut system. Now, if I open up these cuts a little bit, let's call that the plus side and the minus side, plus side and minus side, and so on. Then I can glue together these two sheets. So these are the same point, and then I simply glue the plus cut here to the plus cut here, the minus cut here to the minus cut here. And so what I've done is I've glued in a tube. Okay, and so on. And so if I redraw that, what you see is I have a genus G equals n minus 1 surface. Okay? And so I've demonstrated topologically now that we've created non-trivial curves. In fact, we can make we can write a nice basis for the homology of the curves as follows. So here's the x-plane. So let's choose our cuts like this. Do it with degree 8. That should correspond to a genus 3 curve. And I can choose a curve like that, curve like that, curve like that, that. Whoops. Well, that one's going to be uninteresting for a reason I'm about to explain in a moment. Let's just stop there. And we can also choose another closed curve that goes like this. It goes like this, but now, when I go through the cut, I pass from one sheet to the next sheet. So let me indicate that with a dashed line. But when I pass from the cut again I go from the dashed sheet to the original sheet, so this is a closed curve. And similarly, I can draw a closed curve like this, and a closed curve like this. Now, in terms of these other topological pictures, what we have is a genus 3 curve. I'll explain how we compactify x in a second. And these correspond to curves that look like this. That takes a little thinking to go from this kind of picture to this kind of picture. But to make it plausible, look at the intersections. We can orient these curves. So let's agree that the orientation is on the on say the plus sheet where I have solid lines. With the right-hand rule pointing out of the board is a +1 intersection, and the other way is a -1 intersection. Well, you see this has intersection, this curve, alpha 1 has +1 intersection with beta 1 and 0 intersection with everybody else. If I did it right. Yeah. Yeah. So the blue obviously doesn't, I mean, that's completely obvious from the way I drew these curves. So similarly, we have alpha 2, beta 2 here, alpha 3, beta 3 here. Okay? And these form a basis these alpha I and beta I form a basis for H1 of this curve of genus 3, and they correspond to the abelianization of the alpha i's and beta i's that we had before when I gave you the relations for pi 1. Okay. Now, here I've assumed that n is, here I've assumed, sorry, this was m. M was this. Here I have assumed that the degree of p is even. If the degree of p is, say, 2m plus 1 is odd, then we always have to have a cut that goes off to infinity. So if we have free roots, for example, then we have to take a cut which goes off to infinity. So to describe what's going on here, it's good now to come to Pan's question and say, how do we compactify this curve? So we're looking at sigma, which is the set of solutions of x and y, such that y squared equals p of x. And let's let p of x be a naught plus a1x plus dot 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 plus an x to the n, where n can be even or odd. Okay, what happens at x goes to infinity? Well, in the case where the number of roots is even, where the degree of p is even, you would expect that these just go off to 2 points at infinity. Okay? This complex plane has its point at infinity. This complex plane has its point at infinity. And they're just 2 points that I have to add to compactify this curve. That's what you expect from this picture. If the number of zeros, or the degree, is odd, then I've got, you would expect there to be a branch point at infinity. And with a branch point, we should be only adding 1 point to compactify the curve. So let's see if that happens. Well, from this equation, we can see that y goes like plus or minus the square root of a n x to the n over 2 at infinity. Okay, so y goes to infinity. So if n is even, we can change coordinates. We can say w equals 1 over x. That's the right change of coordinates to compactify the complex plane, the x complex plane, to CP1. And then we can let v be y x to the n over 2. And it's even, so that's an allowed change of coordinates. So what is our equation then? Our equation becomes v squared equals an plus an minus 1 w plus dot 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 plus a naught w to the n. So x equals infinity, the neighborhood of x equals infinity, is w about equal to 0. And now, look, indeed. Of course, an is not 0, because I said the polynomial has degree n, so that means that an is not 0. So what I have then is 2 distinct solutions at infinity, 2 branches at infinity. We have v equals plus or minus the square root of an. And that's perfectly consistent with what we expected from this picture. This sheet has 1 point at infinity. This sheet has the other point at infinity. So what I've done then is I've put in 2 points, just 2 points, and I've compactified that curve. So if I'd been a little more honest about this picture here, there would have been something like 2 points here, which are the points at infinity, which I've added in to get a compact genus 3 Riemann surface. If n is odd, okay, so then we know that we have to have a cut going off to infinity. So what do? Well, let's we let w equals 1 over x. V is y, w to the n plus 1 over 2. And then, okay, so, yeah, I'm running late, so I'll skip the steps here. So v squared is then anw plus an minus 1 w squared plus dot 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 plus a naught w to the n plus 1. So you see, in order to make a good change of variables, I need the n plus 1 in order to divide by 2. So what I do is I substitute x equals 1 over w, multiply through by w to the n, but then I want to define this new v, so I have to multiply the whole equation by w again. And that's why there's a w here. And that w makes a big difference. Because now, near w equals 0, we indeed, remember an is not 0, we indeed have a branch point. The projection looks like v squared goes to v squared. Okay? V squared equals w. So we have our branch point at infinity. And so we add one branch point, one ramification point at infinity. In either case, the genus, to summarize, the genus is the degree of the polynomial minus 1 over 2, greatest integer. Now, a little exercise that's good to do. Suppose n is even. You can embed this curve into weighted projector space with weights 1, n over 2, 1. So think of this as capital X, capital Y, and capital Z. And this projects to CP 1, 1. Think of this as capital X and capital Z, away from the point 0, 1, 0. So we talked about weighted projective spaces. And so you see, if you have those weights, then you could write a curve in weighted projective space. Y squared equals a naught z to the n plus a1 z to the n minus 1x plus dot 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 plus a n x to the n. So that's an equation in homogeneous coordinates, which in the patch z equals 1 is exactly our equation when we choose the gauge, z equals 1, is exactly the equation we had over there. So this sigma embeds into here. This is a compact space, and so you compactify it by adding these 2 points. Okay, one last, sorry to go on so long, one last point, which I want to use in a later remark, and that is about these alpha and beta curves. So I said that these alpha and beta curves form a basis for this homology, and the thing I want to stress is that H1 of sigma is a lattice. So I can add these curves, and there's an intersection product. There's an anti-symmetric intersection product. And it has an anti-symmetric, an integral anti-symmetric intersection product. So I have these curves, and I have some intersection product. I choose an orientation, and I know how to assign a plus minus or a minus 1 to each intersection. And so I have this lattice of rank 2G, and it has an intersection product. Now, the thing I want to remark is that everything here depended on P. right? So the positions of these roots tells me what P is. P is some non-zero constant, say P naught, times the product of x minus rho I equals 1 to the degree of P. So the whole thing fibers over the space of polynomials with simple roots. So if I change P, then the roots start moving around. Then these curves start moving around. So the picture you're starting to get is over the space of polynomials, I have a lattice that's moving around. It's the lattice of these cycles. And what I want to show in a remark, maybe in a lecture or two, is what happens when you go around a singular place where two of these roots coincide. So I stressed that it was very important that the roots were all simple roots. But if you think about that, what is that? That's the space of complex numbers where no two of them coincide. So clearly that's not a simply connected space, because there's a locus where two of them coincide. So we have another interesting possibility of monodromy in that space of these polynomials with only simple zeros. Okay. Next time we're going to begin, before we talk about that, we're going to begin with another aspect of bundles with discrete gauge group, which is actually the notes I handed out today, which is I want to show you the basic principles of gauge theory, which I can just illustrate already now, now that we know what a bundle is with a discrete group. So we'll talk about gauge theories with a discrete group.